Meet SolarEYE, a measurement tool that combines luminescence imaging, IV, resistance measurements, and finite model computation to render rapid diagnosis of each solar cell that points out process-related limitations to cell efficiency and calculates room for improvement compared to the best in class. A luminescence imaging setup consists of the wafer or solar cell, which may be under electrical contact, a camera, and a monochromatic light source, like a laser. If we drive current through the cell, the injected excess carriers may radiatively recombine and emit IR photons that's close to the bandgap. This is called electroluminescence. The camera image of this emission pattern is a little bit like an X-ray for solar cells because it indicates the internal voltage. It's a very good indicator of the health of the solar cell. We may also inject excess carriers by illuminating it with the laser. This is called photoluminescence. Now, there are many published methods to analyze these images by separating out the contrast in recombination and series resistance. But these contrast images are still a few steps removed from enabling the user to make key decisions. For example, we would like to trace the contrast images to process-related parts, breaking down the series resistance into metal line resistance, contact resistance, and so on. And we want to find out underlying factors to recombination, like the aggressiveness of the metal print and recombination currents at the wafer edge and periphery and so on. Next, we would like to quantify exactly how much these different factors are impacting cell device characteristics like fill factor and open circuit voltage, so that we can identify important things to improve. And then finally, it will be great to make some prediction of the actual improvement in efficiency if we had changed the value of some of these parameters to state-of-the-art for the class of cells that is in study. Because that is the basis for critical decision making, which translates to dollars per watt. Now this is where SolarEYE comes in. SolarEYE combines measurements with a powerful computation engine to do the calculations necessary for the end goal. The first step involves auto-fitting of device parameters to the luminescence images and other measurements. The basis behind the computational engine is a detailed finite element model of the solar cell, which is almost an exact replica of the real thing, down to the level of details like finger number, wafer shape, busbar shapes, rear solder pad layouts, and so on. This finite element model simulates the luminescence patterns as well as other available measurement data and combines them to the measurement to test goodness of fit. Over a few iterations, the computational engine will auto-fit the underlying device parameters like contact resistance, metal-induced recombination, edge recombination, until it arrives at a good fit. At this point, we arrive at almost a complete model of the solar cell with the correct parameters to describe it. Next, SolarEYE performs a loss analysis based on the extracted parameters. Loss analysis puts the results into context by simulating the actual impact on cell open circuit voltage and fill factor. The first pie chart here describes the relative importance of different recombination currents on the open circuit voltage. Here you see that because we have a standard aluminum BSF cell, the combined contributions due to the front emitter and base are rather high, which is not too surprising. But more insightful is the realization that the front metal print also contributes significantly to limiting the open circuit voltage. So that says something about the combination of the metal paste and firing conditions, as well as the emitter profile. Next, SolarEYE displays a waterfall diagram of the fill factor. On the left-hand side is the theoretical value of fill factor for a perfect solar cell, and on the right is the actual measured fill factor of the solar cell. The first bar sums up all the series resistance factors which limit the fill factor. It's about 2.5% drop, which is pretty typical. Within this bar, we can see the split due to contact resistance, finger resistance, and emitter sheet resistance. The other bars have to do with depletion region recombination as well as non-uniform recombination at the wafer edges and periphery, which further drops the fill factor into the final 79% range. we can see that edge recombination contributes significantly. So in this diagram, the contact resistance and edge recombination are two components related to the metallization, edge isolation, and PECVD, which can then be tuned to raise the fill factor. Finally, the most exciting feature for SolarEYE is the simulator. This is the part that does the predictions of cell efficiency improvements. By default, SolarEYE will compute reasonable improvements that can be expected by changing the cell parameters to typical or best in class. It puts the results together into an easy-to-read chart that indicates how the efficiency can improve with respect to these changes. So in this example here, we're starting off from a 18.2% multicrystalline cell. Base recombination is fairly typical, and the rear aluminum BSF firing is well optimized, so there's not too much improvements that can be expected from improving the base. On the other hand, there is much room for improvement in the emitter, either by optimizing the diffusion process or passivation, with a room for improvement by almost 1%. Switching the front metal paste or improving the emitter and print firing processes can reduce the front metal induced recombination and front contact resistance to more respectable values, with room for improvement by about 0.3% absolute. So this gives us a kind of roadmap towards how to get our efficiency up by more than 1%. In this case, the optimization of the passivated emitter is key. SolarEYE is automatic, so that the user doesn't have to go through the hassle of setting up the simulations and looking up literature for state-of-the-art solar cell parameters. The SolarEYE measurement routine and auto-fit features runs at the click of a button. On an affordable workstation, the entire iterative fitting routine completes in about 3 minutes. The results are then organized together to give you the loss analysis charts. And then optionally, upon choosing the type of solar cell under study, SolarEYE performs efficiency improvement towards more optimized parameters. So whereas this whole process of measurements, analysis, literature search, computation, simulation, compilation, and reporting used to take days by an experienced photovoltaic scientist, this can now be done in your own lab or production floor at a speed that gives you instantaneous insights and feedback. The underlying cell parameters like contact resistance, metal-induced recombination, and the recombination under the passivated areas can also be monitored over time and treated on a statistical basis, for example, correlating them to process parameters. These underlying latent variables are often better correlators to processes than IV characteristics, for example. SolarEYE comes with different measurement and analysis routines so that it may not only analyze a finished solar cell, but it may be comparing the solar cell to midstream samples of precursors for a more comprehensive analysis of the losses in the different parts. The advantage of photoluminescence is that it's contactless, so that for this example of an N-type bifacial solar cell and related midstream samples with the front or rear grid omitted, SolarEYE can compare the samples, auto-fit to all the photoluminescence images of all samples for a more accurate separation of losses due to metallization and edges. So here we show for the example of the N-type cell, the corresponding loss charts and the efficiency improvement diagram. We may be also looking at a localized BSF cell or PERC cell together with its midstream samples, so samples without the front grid and also samples with no rear laser dielectric opening. So again, SolarEYE gathers the photoluminescence images of each, auto-fits to all of them based on a common set of underlying parameters, and then uses them to construct the loss charts and the efficiency improvement diagram. In the last example, we're back to a normal monofacial aluminum BSF cell, and here again we can have two samples, one being the finished solar cell and the other one being the cell without the front grid. And by this measurement routine, we have more data to fit to, and therefore a better separation of the contributions due to metal-induced recombination and wafer edge recombination. And again, we end up with the loss charts. I hope that gives you a good impression of what SolarEYE is and what it does. As computational powers improve and machine intelligence finds its way to different applications and different areas, I hope you take the next step with us in using SolarEYE to measure and make decisions on your production floor or lab.